The Rayleigh criterion, I will show actually the Rayleigh criterion is wrong. There are better criteria, but that's the only thing we have. Because as soon as you talk about criteria, as I've shown, it's just a qualitative way to understand instabilities. It does not tell you how to suppress them. I will show an extended criterion, but in practice, everyone is using the Rayleigh criterion. It's just the way it is. For example, if you want to have a good Rayleigh criterion for a real gas turbine, you should know also the dissipation. So you should include the Helmholtz resonators, the inlet and outlet impedances, and all that. So that's where it's getting complicated. Other questions?
Talking about the Rayleigh criteria, what I understand is that it is appropriate to take the volumetric sum. Like you talk about a volume, you know the total Q prime and P prime.
Yeah.
Then you integrate.
Yeah.
But often in experiments, it is difficult to get planar images, 2D images, and so how do we define is it right to talk about take 2D plane and talk about
Well, I've not defined the Rayleigh criterion yet. Okay, I'm going to do it in 10 minutes, but it's local, and at every point in the flow, you have one Rayleigh criterion, and then you have to integrate over the whole domain, and you have to integrate over time. And the Rayleigh criterion in most flames is not like, it's not like you have a big plus here for the Rayleigh criterion. In most cases, when you compute the Rayleigh criterion, you're going to find plus, minus, plus, minus, minus, plus, plus, plus. And the integral is going to be slightly positive. But there are zones which damp the flame and zones which push it. In other words, coming back to the swing, there are some places of the flame pushing the swing and some places going against the swing. I will actually show examples where combustion can stop a commercial instability. If you release heat at the wrong moment, then you can stop the commercial instability. So the Rayleigh criterion, I will talk about it later. I mean, the Rayleigh criterion is a strange quantity. Okay, we take a short break, and we come back in 10 minutes. Thank you. So, now we're going to start describing the methods, okay, which is a different problem now. We have finished the phenomenology, so, basically saying the general things about flames and commercial instabilities, but we need to start talking about real business now. How do we study these things? So I will have to start by acoustics, which I already started actually yesterday. I will do acoustics in non-reacting flow, then we'll go to flames, acoustics in flames, which is an interesting topic. And I will show you the methods to look at the interaction, the boundary condition, the impedances, what we call flame transfer functions, the Rayleigh criterion, and I will then describe the tools which are needed if you want to study commercial instability. Some of these tools are extremely simple. They correspond to theory, like those I have described during the seminar. And some are, of course, extremely complicated, like LES. And there's a whole range in between. So let's start by what I did already here. That's the acoustics in a non-reacting flow. Just to remind you how we did it, we normalized everything by the mean values, looked at the perturbations. We wrote the perturbation of pressure and velocity. We suppose the flow was isentropic because if it's non-reacting, entropy is constant. We created the wave equation. We said that there was two solutions, the wave going right and the waves going left. And the general expression was this one. And you have these waves everywhere. Okay, this I have already shown you. Just need now to elaborate a little bit. For the wave going right, you see P prime and U prime. If you do the ratio of P prime divided by U prime here, you find exactly rho C. So that's the impedance in a tube where the waves are going only in the right direction. And vice versa, if the waves are going left, you have an impedance which is equal to minus rho C. And in general, if you want to define what's happening in a tube, the acoustics people, they like to work with this impedance Z, which is a useful quantity, especially for boundary conditions. So in the general case, the impedance of a given surface is the ratio of P prime over U prime. And physically, sometimes it's more meaningful to define what we call a reflection coefficient. The reflection coefficient gives you the amplitude of the reflected wave divided by the amplitude of the incident wave. Since the reflected wave F is equal to P prime plus rho C U prime, and the reflected one is P prime minus rho C U prime, you can prove easily that the impedance is rho C 1 plus R divided by 1 minus R. So giving the impedance of a surface is the same as giving the reflection coefficient of this surface. And you're going to need them when we do flames. Now, I've already described this yesterday or the day before. This is the energy equation for a non-reacting flow. I've told you that this thing was not changing in these systems where you have simple impedances. I was using this demonstration yesterday for CFD, but now I want to extend it to do this I've said already, to do the same thing for flames. Okay, so which really means now I'm going to talk about acoustics in reacting flows. We want to do now the same thing. We have a burner, and we want to look at the acoustics in this burner, but now there is combustion. How do you do that? Well, you keep the momentum here, and you keep the continuity. You need them. But then you have to add one equation for energy or temperature. Here I've taken the simplified energy equation. Here this is the heat release. And here you need to keep the compressible terms, of course. So now if you want to normalize that, you need a little bit more efforts. How do you do that? You say that the density will be the mean density plus rho prime. P will be P naught plus P prime, and T will also be T0 plus T prime. And you plug these things into the previous equations, and you remove all the second order terms. So you're left with the continuity equation and the momentum equation which we had before. Nothing new there. But then you have, and the variables will be rho prime, U prime, and P prime this time, because P prime is not anymore related to rho prime like it was for the asymptotic case. And the temperature equation is this one for perturbation. You also normalize the state equation, and when you combine all that and you introduce the sound speed, you end up with this very cute equation here, which is almost the one we had before. ddt of this thing, which is the acoustic energy, plus the flux, which is fine, equal a new term here. This equation is the basics of most theories for combustion instabilities. It tells you that the acoustic energy in a combustor changes because of fluxes on the boundaries. In other words, the energy can leave by the inlet or leave by the outlet, or not, depends. And there's a source term now. This term was not here without combustion, okay? And the source term is a constant here, gamma minus 1 over gamma p, that's constant, multiplied by p prime omega dot prime. And you see that p prime omega dot prime is the product of the unsteady pressure by the unsteady heat release. Okay? These two things multiplied, that's the source term. So you can do what I've done before, that you can integrate this equation over space to obtain this equation. The time derivative of the acoustic energy in a combustor is driven by the flux of energy on the walls and a source term now, which is the integral over the whole domain of what we will call the Rayleigh criterion, omega prime p prime. And now you can say, exactly like we did for the swing, you can use this in equation to directly give a stability criterion, which tells you that if this term is positive over a sufficiently long period of time, then the energy will grow. That means your system is unstable. And that's the famous Rayleigh criterion, saying that if you want instability to occur, you need integral of omega prime p prime dv positive over the whole domain. Doesn't mean it has to be positive everywhere. It's only the integration over the whole domain. So exactly in the same way that we had Fv must be positive for the swing, we have omega prime p prime must be positive for combustors. Okay? Remember that this we did assuming that there are no losses. In the swing, if this thing is rusted, you're going to need more energy. It's the same thing here. If you lose acoustic energy somewhere, you're going to need to put more energy into the omega prime term. Now, this thing was written by Rayleigh in 1878. I mean, that's a pain. I mean, these guys understood many things already, except he didn't say it that way. He had this very funny English saying, you know, if heat be given to the air at the moment of greatest condensation, which means highest pressure, so if omega prime is in phase with pressure, or vice versa, then the vibration is encouraged, and vice versa, of course. If this thing is negative, you will damp the instability.
But this, it is by his intuition, or he has actually written these equations and forgot in his
I don't think the equation is there. I think it's purely intuition. Yeah. That's a good question. Actually, I would have to go back to the paper to look at that.
So he was not the equations of
Yeah, these guys didn't write many equations. Huh? They had a feeling for it. That's the nice thing about it. So, are these acoustic waves a problem? In general, you have acoustic waves in a burner. They are not a problem if the Rayleigh criterion is not satisfied. You have a spectrum, which is the one I've shown you before. It makes noise, broadband noise, and that's all.
The theory of sound by Rayleigh,
Yeah,
I think it gives some kind of mathematical.
yeah, it's true. Well, there are a few equations. I'm not sure if there is an equation for the Rayleigh criterion exactly.
Yes, given mathematical.
The derivation?
Called theory of sound.
Yeah, I think I will check. I have the paper here. It's a good question. So in many cases, if the Rayleigh criterion is not satisfied, the only thing which happens is that we have a flame which makes noise, not too much noise. But if the Rayleigh criterion is satisfied, then it becomes unstable, and then this flame here will change its spectrum, and in addition to broadband, you will start seeing peaks, which are exactly what Professor Koushawi showed yesterday. He had broadband noise, and he had a huge peak, if you remember here. He didn't call it instabilities, he called it hooting, but you know, I think it's the same thing. This is the trace of a strong resonance in the system. Now, some scalings here. We have talked about turbulent combustion. It's important to realize that when you have an instability in a system, the velocity which is induced by acoustics can be very large. I've shown you already that there is a scaling between P prime and U prime. The scaling is that U prime is 1 over rho C P prime, something like this. So if you have a pressure amplitude PA, you can guess how much acoustic this gives. It's useful scaling. So in many burners, you have heard yesterday levels of the order of 150, 180. Actually, there are burners which go to 200 dB, decibels there. You know, you can go from dB to Pascal with this formula. If you take 20 log of P prime over 2 to the 10 minus 5, you can go back and go from decibels to pressure. So for example, if you have 200 dB, you plug it here on that side and you can find P prime. P prime will be, you know, of the order of 1,000 to 20,000 Pascal. Now if you know that P prime is this much, you can guess U prime. And U prime will vary between 2 and 20 meters per second. So that's important. It's a big velocity. So that really means that first, these velocity fluctuations, they are larger than most turbulent velocities. So we've been talking a lot about, you know, the effect of turbulent velocities, but now we have something larger than a turbulent velocity. So it will change a lot the combustion in the system. It will actually change it so much that this velocity can be even larger than the mean velocity, which brings us, you know, to what we said last time. The inlet velocity might be changing sign. Okay, so the flow might be leaving the burner by the inlet, which is not a good news. People working in industry will tell you that quite often they find soot on the wrong side of the flame tube, okay, which is also an indication that the flame, instead of staying in the flame tube, can flash back, and that has to be due to commercial instabilities. Now, this is again the picture I've shown you before. I wanted to show you how the flow looks like when it becomes unstable. That was the stable regime. And if you go to an unstable regime, this is the kind of flow you will see. So with naked eyes, you will see combustion all over the place, and that's a usual feature of gas turbines. People will tell you, oh, when my flame is stable, it's a long flame, but when it becomes unstable, I have these two big zones of instability here, and everything is very bright. So it's very bright also because now the heat transfer is very large, and the lifetime of the chamber diminishes a lot because the heat transfer is very large. And the flame is much more compact. So it's good for efficiency, it's not good for the structure. If you do a high-speed visualization of this flow, this is what you find actually. You see this huge vortex here, mushroom vortex, which is created. And if you do a cycle on that, you see that this is a small vortex initially, growing more, and then interacting with the neighbors, and this cycle turns at 530 Hertz. So you see it's a very strong modification of the flow there. Now it can go even more. You remember this movie I've shown you. In that case, you can have flashback here because the velocity, the mean velocity here is less than the acoustic velocity. And if this happens here, when you see here the flashback, like now, shoop, it really means that you have the mean flow this direction, the acoustic velocity in the other direction, and the flame is just carried. It's not even, doesn't even have to be propagating. If the acoustic speed is 20 meters per second, the flame speed is only 20 centimeters per second. So it's not really propagating, it's carried away in the wrong direction. You can imagine when you design an engine that you don't want the inlet to be an outlet. It shouldn't go that way. Huh? Now, another thing also which is funny, well, funny, interesting with instabilities is that even instabilities are unstable. You will hear actually for this burner, where the flow is injected here, it's a swirl burner, you will hear multiple noises. Don't change anything, it's the same regime. And so then you can talk to people, actually Sujit here is a big specialist of that. You can have bifurcations during instability. So if you listen to it carefully, you will recognize different modes now. So as you heard, we had low frequency modes, high frequency modes, and the flame was alternating between the two. We don't change anything. So that's a problem because it means that if you look at an unstable regime, you might have more than one instability which can appear for this regime, and the modes are competing. Whichever mode is most amplified takes over for a while, then the other takes over. So that makes things even more complicated. Now, you don't need to pay a lot to do instabilities, okay? If I wouldn't have taken the plane, I would have taken this with me when I give this course. You go to any shop and you buy one of these small flames here that you can use, at home, and you can put it in a tube. So this is really what industry is doing. I'm doing it in France, so it's my own business. Here, this is a burner, and this is a combustion chamber. This is just a tube. Of course, in a real engine, everything is much more expensive. The combustion chamber is very expensive, and the burners or the burner are also very expensive. But if you just take one of these three, and you take, for example, this flame and take the short tube, and you put it on top of this burner, this is what you do. And you see that when you put this burner into this chamber, not much is happening. Then you take a long tube, and this is what's going on. Not much, okay? So if you're in a company, the first year you have sold to your customers the short tube, the second year you have sold the long tube. So if you believe in linear systems, you say, now I'm going to sell you the medium tube on the third year, and I guarantee that nothing bad will happen. So you sell them the medium tube, or you sell it to another customer. And then suddenly something happens. So you see this tube is actually, it's this guy here. It's this one. So this one doesn't make noise, this one doesn't make noise, this one makes noise. That's good for us scientists, because right away it's telling you that it's not going to be simple. It's not as if you can say, short tubes are unstable, long tubes are unstable. No. Short, stable, medium, unstable, long, stable. There's something basic here going on that we don't capture with linear ideas, saying, oh, this is too short, or this is too long, or this is too fast. I mean, you have to do some more theory to capture that.
So is the flame coming in L by 4 here with the medium tube?
The flame is doing?
1/4 of the length?
Well, yeah, not far from that. This is actually a view of the flame when there is no instability. You see here the flame. This is now a quartz tube, a little bit more expensive. Okay, you need $1,000 to do that. And you see the flame is moving a little bit. But when you go to an unstable regime, then you can see the flame now flashing up and down. And when you go to a very strongly unstable regime, you start recognizing this mushroom-shaped flame fronts here. And so the flame is oscillating at the frequency of the mode that you can hear. And the mode is not very far from the acoustic mode of the system. I will show that later today.
So in the flame shape you're showing the cylindrical thing. We could have done experiments on M-type flames, N-type flames.
Sure.
What's
For,
the difference in like different modes?
for swirl flames. For a swirl flame, yeah. For these flames, there's only one shape. It's always a V flame for that case. For swirl flames, yeah, sure, that's due to swirl. Swirl will make things much more complicated. So you can have M flame, V flames, all kinds of things. These flames are very, cones. Okay, so let's go now to the methods. There are two classes of methods to do studies of combustion instabilities. The first one is full CFD, and the other one is what we call acoustic codes. Acoustic codes are actually, if you simplify them even more, you can go to what I will show to be analytical methods, something you can do by hand. So, the starting point of that, again, is to recognize that in the Navier-Stokes equations, you have everything. Okay, you have acoustics, you have flames, you have turbulence, everything. So if you solve the Navier-Stokes equations, you're good. You cannot solve the Navier-Stokes equation, but you can do LES. If you neglect the small scales of turbulence, which are probably not that important for combustion instabilities, you can build a compressible LES code, and this code will predict combustion instabilities, and we have done it many times. But it's a very expensive way to do business. There's another way, which is to freeze the mean flow, neglect viscosity, and linearize, and then you will find what we call acoustic codes. Still a 3D code, but much faster than the turbulence codes. So what's the difference actually between what we did for turbulence models and for acoustics? So this is the momentum equation. In both approaches, we have written that the equation has the mean value and the U prime. When we did turbulence models, we kept the nonlinear terms, and we say, oh, those nonlinear terms are important. And when we do acoustics, we actually remove them. Okay? So it's the same starting point, but it's different tools here. LES is going this way, acoustics is going that way. Then you might say, oh, which one is good? Well, both are good depending on what you want to do. In the acoustic world, you are limited to small amplitude of U prime. You have to know that from day one. If you have big amplitudes, this is not applicable. If you have small amplitude, it's a smart way to do business because it is cheap. And of course, price is going to be important. So here, on this line, we are really in the field of LES, and that's going to be expensive. Here on this line, we're going to have linear equations, so we're going to be able to solve them much more easily, either in the time domain or in the frequency domain. And actually, since we started that way, you might even simplify everything, go to 1D cases, and solve them by hand, which is what I will do later. So again, to remind you of that, LES can be used anywhere along this sequence, but acoustic codes can be used only in this zone. So now if you talk about acoustics, the acoustic codes, there's an interesting problem there. You say you want to do acoustics, but there is a flame there. What do you do with the flame? It's a big problem. So the flames actually are modeled only, well, there are two effects. The flames are modeled through two effects. The temperature is changing, but that's easy to account for temperature changes. You just need to change the sound speed. So that's fine. The first difficulty now is really to model the active effect of the flame. The flames are loudspeakers, they're blue, blue, blue. You need to put that in the model. So how do you do it? Well, if you look at the global loop, which we have in those problems, we are able to cut it somewhere. So the way we're going to cut it is we separate in this phenomena, we separate things which are acoustic from things which are not acoustic. So how do you cut that? Everything here, the generation of the pressure wave, the convection, the propagation of the acoustic in the system, and the change of flow rate at the inlet, everything is acoustic. So this can be completely solved in the acoustic world. On the other hand, the fact that you create a vortex is really a flow problem. The fact that you burn this vortex after a certain time is really a combustion problem. And this is not acoustics. But you can completely replace all this box here by a simple equivalent model, which tells you, if you tell me what is the inlet velocity perturbation U prime, and what this U prime is creating as Q prime, unsteady heat release, then everything else here I can take care of. And that's the basis of the Crocot approach. Crocot said, if you can write a relation between Q prime and U prime, everything's solved. So you see all the complexity of vortex formation, chemistry, everything else, is here. You have taken it out of the acoustic world, and then you can solve the equation in the acoustic world. That was the main idea of Crocot more than 60 years ago, and we're still working with that. So why is it so? This is the equations I wrote before for the acoustics with combustion, and remember, that's the normal equation without flame, or with flame is the same. And here, the only additional term in this equation is the unsteady heat release. So if I know the unsteady heat release here, I can completely close the acoustic equations and find a much simpler solution to my problem. Now, what does really an FTF measure? That's huge discussions in the community about that. A priori, it seems simple. You give me a U prime, I give you a Q prime, and I will tell you also two things. If n is big, I will tell you, oh, be careful, because any small change of velocity here is creating a big change of Q prime. That's dangerous. And then it tells you also something else, tau. It tells you if you create a velocity perturbation here, it will take tau milliseconds for the flame to react. And this tau, from control theory, it's easy to feel that it's going to control stability too. So n measures the strength of the response, and tau measures the delay of the response. And I repeat that this n and tau contain everything. They are functions of frequency too. If you do that at low frequency or at high frequency, you won't have the same result. So where are we now? I said everything is in the Navier-Stokes equations, and then if you want to go the expensive way, you do LES. If you want to go less expensive way, you go acoustic codes. And if you just want to look at criteria, you do what we call the energy method. So we have all these tools available. Which one should you use if you have a problem? Well, the Rayleigh criterion really never explains anything. It's a good way to check that, if it's positive, then it's unstable. It won't tell you why it's positive. It's just an observation. So many people, actually all people, 99% of the people writing papers on thermoacoustics talk about the Rayleigh criterion, but doesn't help you that much. These two things are what you need if you want to look really seriously at commercial instabilities. You need a good LES code and you need an acoustic code. So let me start with giving you a few examples of how you handle those things. I'm coming back to this tube here, which is the most classical example where you can actually use the Rayleigh criterion to guess if the system is unstable or not. I'm going to do it by hand for you so that you see it's not that complicated. So you take the tube, you say it's an open end here going to the atmosphere, and it's an open end at the basis going to the atmosphere. So we know that pressure will be imposed here and there. And here we have a place where we are going to release energy. You can put a flame here, like I did. You can even put, electric resistance, which generates heat. That's how Riquet did it. And that will give you the same answer. So that's a homework. Normally, could have been the control, actually. The problem here is to derive the expression of the first acoustic eigenmodes here. And then if you assume that heat is related to velocity in this way, to show when this tube will be stable or unstable. We're going to take a tube of 1 meter and a cold sound speed of 340 meters per second. So first problem is, suppose there is no resistance here. What is the acoustic eigenmode of this system? The way you do it, you start saying that P prime is the sum of two waves, A going up, B going down, so it's written like this, and U prime is this expression with a plus. Okay? Always the plus rho C for the wave going up, minus rho C for the wave going down. You apply the boundary conditions here at the top and at the bottom, and it gives you imposed pressure. Now, if you write this condition here in this expression here, it tells you for x equals 0, for all times I must have P prime equals 0, so A minus B must be 0. So this gives you A equal to B. And if you go on the other side, here, you say at x equals L, pressure must also be 0. You plug that into this expression, and you see that since A equals B, you must have sine KL equals 0. Now, it's only one way to do that. KL must be equal to pi. That's the first mode. So the length of the burner must be 1/2 the wavelength. That's what we call the half-wave mode. Okay? There are cases where you have the quarter wave mode. This is the half-wave mode because the only way to fit a mode, an acoustic mode, if you have here P prime equals 0 and here P prime equals 0, the only thing which fits between these two, the first one is this one. Okay? So lambda, the wavelength is equal to 2 times L. Okay, that's the half-wave mode. And once you know the wavelengths, you can compute the frequency and the period, and you find the frequency of 170 hertz and 6 milliseconds. And you have supposed, and it's almost true here, that the sound speed is constant. So it's a flame which doesn't generate a lot of heat. If I have now this information, I can construct the pressure and the velocity signals here in my domain. So this is going to be the pressure, and this is going to be the velocity. Everything is determined up to a constant because it's a linear problem, so I don't have any reason to fix A. I could have set it up to 1. So the structure will look like this. At one instant, pressure will look like this, and velocity will look like that. Pressure then will move on the other side. Velocity will move on the other side. Okay. That's without flame. Now, suppose you put a flame there. At x equals A, we install a flame front or a heat release, let's say, and we're wondering about what's going to happen. So if we look at the signal in time at point A here, you see pressure oscillating and velocity oscillating. So this is the velocity oscillating at that point, and this is the pressure. It's a sinusoidal signal. At point 8, it's at the upper half. Point 2 is at the bottom. And now we add combustion. Suppose the temperature does not change too much, and suppose the delay is this one, 0.2 times T. And we plug this expression here. So that really means that Q prime will lag U prime by a time tau. So if we know U prime, and we assume a small perturbation for the moment, you see that if we are at A over L equal 0.8, that means we are up there, this is going to be the velocity. This is going to be the pressure. The heat release is lagging the velocity by tau. So this is velocity, this will be heat release. Heat release now at that point is this curve, and pressure is this curve. You see that they are not really in phase. You can actually write the product of this curve by this curve to look at its sign, and you find this curve. This is the product P prime, omega prime. And you see it's negative all the time. So in this case, you can say that for this flow and this flame, if you put the flame at the top here, in this zone, there will be no instability. Now you can do it on another point. If you take now a point which is at A over L equal 0.2, this is what you obtain. This is velocity. Behind it, you see that heat release is there, and then pressure is this curve. And you see that now pressure and heat release are almost in phase. So if you measure them, that's the Rayleigh criterion. It's going to be positive all the time. So it's telling you this case can be unstable. Now I've done it for 2 specific cases. You can do it completely for any point by constructing the general formula for P prime Q prime. And you will see that this term is positive if sine 2kx is positive. In other words, if x is less than L over 2. And that's the usual result in those things, is that if you have a tube like this, the flame or the heat release should take place here. If it takes place here, and if the delay is small enough, then you will have an unstable mode. So you can see that with the Rayleigh criterion, you can say a few things on a few specific cases if you assume the solution to be known and not to be too far from linearity. That means from the case without flame. More generally, it doesn't mean that all tubes will oscillate when x is less than L over 2. You still need to check exactly the fluxes of acoustic energy, because here I've said P prime equals 0, but we know it's not exactly true. There are some losses at the outlet, and of course there are viscous losses. But this is a good starting point for Rayleigh criterion. So, yes, you can have the Ricoh tube resonates, you can write conditions. The trick which is more interesting with these tubes is to show that instabilities are not linear in these things. You can have, as I've shown you, as a function of the length of the tube, zones which you have stability and zones which are unstable. So if you combine now a set of flames with a set of chambers, which is what the gas turbine companies do actually what the whole world working in industry is doing every day. You have a chamber, this can be for heat exchangers, for example. You have a burner, you plug it in, and you start it. Well, this combination can be dangerous because in some cases, you can have problems which you did not expect. You know, in industry, if this works and this works, they are not going to guess that this one does not. Okay? And so this is why industry has to worry now about understanding what's going on, because you cannot rely in simple, you know, ideas to know if a burner will be stable or not. Okay, I need to talk about impedances now. When I did the wicket tube here with P prime equals 0 on both sides, that was easy, but in a real system, that's not the case. I mean, the pressure is not imposed this way. So we have to worry about the acoustic conditions in a real engine. And in a real engine, you won't have P prime equals 0. Okay, you will have something different. What will you have? Well, you will have a turbomachinery element, a compressor and a turbine. And usually that's an exciting topic to find the impedances. So here, for example, that's the chamber. You need to know the impedance of this guy. What does it mean? It means if I'm sending an acoustic wave in this direction, how much is coming back? That's a very simple question, you know. Now you go to Siemens, you go to Alstom, these people know how much, but they never publish it, because that's a big, actually it's quite expensive if you want to measure that, and it's also a very important information to know if these systems will be stable or not, because the stability depends directly on this impedance. So that means really we need to know how waves cross turbomachinery elements, and that's painful because, you know, that's a simulation which we do now. If you just look without forcing at a flow like this, it's already a complex flow, and if you start injecting waves, that's the case where we inject here an entropy wave into a water state or stage, and as you can see, it's a big mess. Okay. So, but this is the problem you face now. If you want to do commercial instabilities, you need to worry about this problem. Now, we need now to start talking about something that actually Professor Kouchary just flashed one slide yesterday, but didn't talk about it after that. It's entropy waves. That's also called indirect noise, and that's direct noise. There are two ways by which the turbines, for example, act on the acoustic field. If you send a wave, an acoustic wave on the turbine, it's going to be reflected. That's okay, everyone understands that. But there's a more subtle mechanism. If you send an entropy waves on a turbine, it will create reflected acoustic noise, and that's a major problem. All these waves will hit the turbine, and in the turbine itself, two things happen. The flow is accelerating because of the nozzles, and the flow is turning because of the blades. These two effects, I'm not going to talk about the second one because the first one is already exciting enough. So let me show you an example here of what's happening if you send an acoustic mode into a nozzle. The nozzle here is the simplest prototype you can imagine of a turbine stage. Okay? It's a place where the section diminishes. So you can see the wave here. That's the amplitude of the downgoing wave. And you see it's transmitted. That would be noise outside, but it's also reflected. So we care for commercial instabilities. That's what we want to know. If we do the ratio of this thing to that thing, we have the reflection coefficient of the nozzle. Okay? So we can construct the acoustic reflection coefficient of a nozzle. It's the ratio of how much comes back to how much is going in. This depends on the wavelengths. So it's a function of frequency. Now, the trick is, and the difficulty now is that acoustics go to acoustics, but entropy also goes to acoustics. So let me show you now an entropy wave propagating into a nozzle. So this one goes more slowly because it's convection, but then when it enters here, it creates transmitted noise, transmitted entropy, but also reflected acoustic waves. So if an entropy wave hits a nozzle, it creates a reflected acoustic wave. So it makes noise. And so for commercial instabilities now, it opens a new way. It says that if you have entropy waves created in your chamber, they can generate acoustic noise. And that's bad news because it creates what we call a new type of mode, which we call mixed modes. In a real chamber like this one, you have many entropy waves which are created. You can see what is an entropy wave. It's basically a hot spot. It's a zone where you have more energy, higher temperatures. So in this case, like here, you can see that there are many moments where you create hot pockets, and these hot pockets hit here the outlet blade. And when this happens, they will make noise. You don't see the noise on this movie because you will need to look at pressure, but every time these temperature waves hit a blade, they create reflected noise. And this reflected noise is going to be a problem. Why? Because now, for these mixed modes, you have a new mechanism. So this is the same box as before. Acoustic is the same, but now you can have a different mechanism here. If imagine you create here a perturbation of velocity, that will create an unsteady combustion. But unsteady combustion really means that for a moment you may have warmer gases produced or less hot gases, so that will be an entropy wave. This entropy wave will travel very quietly in the chamber, and then it will reach the outlet nozzle, it will make noise. This noise will come back, and then there's a new loop now, which we call mixed modes, and which creates a new mechanism for commercial instabilities. And that's the problem. An example here, that's actually, I think it's the Rafale engine, actually. I'm not sure, it's one of the prototypes, at least, of the Rafale engine. So you have the swirler here, the choke nozzle, and you inject kerosene. We did a simulation of that thing. It's in GFM here. You can have this paper directly on the web, or you can ask me. And it's an interesting case because it's a case where initially they came to us and told us when this engine has a problem, it has a problem when it's raining. So when the air is dry and cold, and dry and hot, there's no problem here. And if you cool down the inlet temperature, then you start having these instabilities. You have here the pressure field. You can see how the pressure field is fluctuating here, and here it's almost nothing. So if you look now at what's happening, you really recognize these pockets here, which are entropy waves propagating to the outlet. And when they hit the outlet, look at the pressure, you get a pressure wave coming back. So the mechanism is pretty clear. It's these big pockets hitting the nozzle, sending a reflected wave, and then the whole thing gets, self-sustained. So just to conclude, I want to show you how you can model that, because this is an expensive LES, but you can actually replace it by elements. You don't have to do a full LES of that. You can cut the domain in two parts. There's a part here which is a low Mach numbers, when you can just solve the acoustic equations, and that's cheap. And you can also have another part here at the outlet where you solve the nozzle equations. This you can do separately. You can send waves into a nozzle and look at the reflected waves. To do that, you're going to have to couple the model here. Here's the place where you will write the acoustic model. Here's the wave coming out, the acoustic wave coming out, the entropy wave coming out, the acoustic wave coming in. This acoustic wave coming in is the reflection of this one. So it's A in equal reflection of the nozzle multiplied by A out, plus the reflection coefficient of the entropy wave into acoustics. So it's a superposition of the two waves. Now this guy you can have. This one and this one you can have by doing a forced simulation, or there are many things. You can, RUP and ISP, you have them from Marble and Candle theory, you can have it from a computation, or you can have it from full theory of Durand and Moreau here, if you can make it. But these things will give you RUP and RSP. It's not a problem. So you know how much is coming back from the nozzle. Once you know that, you can write the 1D equations here from here to there for acoustic waves, so it's pressure and velocity. You know the boundary condition here. There's only one thing you still don't know. You need to know the amplitude of the entropy wave which reaches this boundary. This is where you need a model. The way we do it, we say that entropy wave which reaches the outlet is the rocket motors are a completely different business. One of the main problems is that the flames are very long, and you cannot use capacity assumptions. And the other problem is what I've shown actually at the seminar 2 days ago, is that the modes are not longitudinal, but they are transverse. So for rocket motors, I think today we have LES, and we have very few acoustic models because transverse modes are a real difficulty. We don't know how to write the transfer function because it's not, here we have a system where basically we say, if I fluctuate the flow rate, I fluctuate the heat release. But now if the instability is transverse, all this disappears. And so rocket engines are much more difficult, in other words.
Sir, how to separate the tan inverter from the rotating mode in case of in the transverse mode?
That's the big question, yeah. For the moment, it's difficult. The first thing you need to do is to compute all these modes. You need to know all the acoustic modes of the rocket engine. After that, to know which one is excited is extremely difficult. You've seen the results 2 days ago. There are at least 10 modes, and they are all transverse, and they all involve also the feeding system, the ducts, so it's very complicated. But it's clearly a field where we need to use all the tools I'm showing here, except here everything is longitudinal, and we have to go to transverse. It's important to say also that these transverse modes are not discussed often, but for example, Siemens or Alstom, when they have a transverse mode here, it kills the engine very rapidly. This is why they need to add Helmholtz resonator here. It's the same for Alstom. So transverse modes are also a big problem, but normally in gas turbines they're able to control it. In rocket engines, the problem is that there's no space to put Helmholtz resonators, so it is a major problem, yeah. It is a major problem. It's not a solved one.
Has anyone done such studies for
Of?
Has anyone done such studies for such simulations for piston engines?
Yeah, that's what I'm going to show tomorrow, yeah. For piston engines, what we're going to have is cycle-to-cycle variations. And this is what I'm going to describe tomorrow.
Not the instabilities, but the instabilities generating from acoustics.
Yeah, well, acoustics are important also in piston engines. You see them if you have a compressible solver. You see the acoustic waves in the engine too, in the intake pipe, exhaust pipe, and in the engine. Especially at high speeds, you see them. For a Formula One engine, you have a lot of acoustics going on in the engine.
In the approach we take, that we solve for the flow first and then solve separately for acoustics.
Yeah.
What could go wrong in that approach? Is it a good way to go, or
That's a good way to do it. But there are many small problems that you have to be aware of. Is that all the acoustic modes I'm describing here are for 0 Mach number. If you want to do what you said, you freeze the flow and you go for the acoustics, you have to say if you do it at 0 Mach number or not. If you don't do it at 0 Mach number, you're basically talking about the linearized Navier-Stokes equations. And we know that solving the linearized Navier-Stokes equations is difficult. This is why we usually stick to say that the Mach number is 0 in the chamber, because it's much simpler. Instead of 5 equations, you have to solve only 1. So if you want to do that, you can, but it's going to be difficult. If you freeze the flow and you solve the Navier-Stokes equation, the linearized form, it's possible. I don't think, not many people do it. Normally they do it in 1D. Even that, we do it in 1D. In 3D, it's really tough, numerically. Yes, yes, yes.
So when you have this flashback, you were saying that in some instances the velocity goes in the other direction.
Yeah.
Velocity.
Yeah.
But then yesterday's lecture, you were saying about how to apply the boundary conditions based on how the information travels.
Yeah.
Now, if I want to do this simulation, then it appears to me that we have to change the boundary conditions.
No. You can't. I mean, if you want to do flashback in the chamber, you have to compute to here. You cannot stop here. Because that's also what NSCBC is saying. NSCBC tells you that if the flow is entering here, or if the flow is leaving, it's not the same, okay? So if you start changing sign in the middle of your boundary condition, that's not good. You should go to a place where you know what you're doing. So you cannot do flashback and stop the simulations here. That's not going to work. So you need to include the domain, the full domain. Yeah. Even with NSCBC, there is no miracle. It's the same at the outlet. You know, if this is an outlet, and suddenly the velocity starts entering, normally you should stop the computation because you don't know what's entering. You know, you have no idea what's entering. So now the code might do something, but it's not going to be smart. I mean, so if it's an outlet, and vice versa. If it's not that, you have to go further away until you find a place where you have a clean boundary condition. I think it's just reasonable.
Have anyone done experimental for the transfer mode or azimuthal mode?
Experiments on azimuthal modes
Yeah.
in gas turbines or in
In Dragon.
rocket? Well, they don't call it azimuthal, they call them transverse. DLR has quite a few experiments on that. I suspect Purdue too, but they don't have a lot of diagnostics, you know. They have maybe 2 or 3 microphones. So it's difficult to say if the mode is azimuthal, transverse, or longitudinal, because the mode is so complicated that to identify the mode, you would need a lot of sensors. I think it's the problem of DLR at the moment. This is why they're working with us. They have a limited number of sensors, and from a limited number of sensors, being able to find the mode is difficult.
How many sensors they use to predict the transfer mode?
Well, for the transfer function, in theory, you need only one sensor for Q prime to have the unsteady heat release, and one usually velocity sensor, which is usually LDV. So you can put an LDV sensor upstream of the flame, and you can do it that way. Or you can have 2 pressure sensors, and from that you reconstruct velocity. So for the problem of the rocket engine is that the transfer function is not well defined. If it's a transverse mode, there is no transfer function. It has to turn and go in the other direction. Which one for? I'm not sure of the question. So you want to know which code to take, or you want? Or the books? I've listed, you know, the books. It depends if you're interested in the physics of the instability, or if you're interested in the simulation of the instabilities. The physics of this kind of animals. That's in chapter 8 in my book, and it's also in Tim Ewan's book. They talk a lot about these things. Then this is really recent stuff. I mean, so you won't find it in many books. You have to go to journals. This is in JFM, for example. And mixed modes, you know, there's another guy. There's a big discussion about mixed modes because there's a guy called Sattelmayer in Munich. And Sattelmayer keeps saying, because he did some of these experiments, that if you make this chamber a little bit longer, all the entropy waves will be dissipated anyway. And so he keeps saying that these entropy modes appear only for short chambers. If you take a long chamber, you never see them. Actually, in the lab, if you have a long tube, you never see these waves because they are dissipated by turbulent mixing. And so there's a big controversy on when we should have them or not. But Sattelmayer is also a place where you're going to find information on that. Sattelmayer, Ewan, and we did a lot of things on that too. Yeah, oh yeah. Well, even this one, you see, this one is really, it's an existing combustor. We were able to publish it in JFM. Of course, if you look at the paper, you won't see any real numbers. Everything is normalized, but that's the engine of the Rafale, okay? So you can find information there on the importance of that. For modeling, it's actually a problem because you need to add a damping factor for the entropy waves between inlet and outlet to account for this dissipation. Otherwise, you find the mode is always unstable. So you need some damping for the mixing. That's difficult to obtain.
You do not have the secondary injection.
Well, that's interesting actually. That was connected to what Professor Kuchari said yesterday. What we see here is that it's really the secondary jets here which cut these pockets. And he was interpreting that in one way. I mean, I'm seeing it in different way. I believe that these jets are what's actually creating these pockets. If the jets here are intermittent, you have a hot jet and a cold jet. If they are intermittent, then you create entropy waves. And we believe that if you suppress this thing, then the mode goes away. Because if you suppress these jets here, there is no mode.
Meaning that if I cut out the secondary.
Yeah, it's exactly what he said yesterday. It's just that we don't have the same interpretation of why. But I agree with him. If you have no secondary jet, for us there will be no entropy wave, so there will be no mode. At least not this one. There might be an acoustic mode, which will be purely acoustic, but the mixed mode will go away. Now, as I said already, it's not, when you suppress a mode in these systems, usually another one appears. It's always like this. So that will cancel this mode. That doesn't mean that if you start a chamber, you will not have another one. Also, you need that for cooling, okay? You cannot really suppress it.
This frequency of oscillation is not the acoustic. It does not.
No, it doesn't, exactly, it does not scale because you're going up at the sound speed, but you're going down at the convection speed. So the lowest frequency here for the acoustics must be 600, and this mode is at 200 because you're going down at the convective speed. This is the key of the problem. You must introduce some convection phenomenon to account for the frequency you see. Otherwise, everything acoustic is like much higher frequencies. Okay, good morning to all of you for this Sunday session. So it will be an unstable session. We'll talk about combustion stability for at least the whole day, maybe even tomorrow. So just to begin, you know that we are in a mechanical engineering department. You know that many of the things we do are related somehow to instabilities. You know, for example, that all the systems which engineers design are built to be in equilibrium. The problem is that when we build a system, we build it to be in equilibrium, but we never really know if it's a stable or an unstable equilibrium. You know, this is a stable case in equilibrium. This one is also in equilibrium, but it's not stable. And that's a major problem in mechanics. In many cases, engineers design things which are more or less stable, you know, like this guy here. And in some cases, the consequences are not too bad. This is flutter on an airplane. But there are other cases which are not as good. Probably you've seen this guy before. Ah, it's not working today. Ah, yeah, this one's not working. That's the Tacoma Bridge. And the Tacoma Bridge was also designed to be in equilibrium. But as you know, it was not a stable one. When there was wind, this thing was beyond stability. And when this happens, the consequences, of course, are bad. All these flows are non-reacting. If you go to combustion, we basically have many things which can be unstable in combustion. Of course, you have flows, and you know that all flows can generate vortices, so that's one instability. If you do two-phase flows, you rely on instabilities to create the droplets. If you do kinetics, I will show in a second that flame fronts can also be unstable, and of course the structures in which we insert our flames can also be unstable. So as a consequence, you can have many instabilities in combustion chambers. They are usually classified according to the size of the system. So going from small to big, intrinsic instabilities are really instabilities which develop at a small level on the flame front itself. So they are of the order of a few millimeters. Chamber instability corresponds to things which happen in the combustion chamber itself, and system instabilities involve the whole engine. In a rocket, for example, this means something where the whole rocket is involved. So just a few examples of that. Intrinsic instability, this is the spherical flame. Now we've talked a lot about it. You know that in a spherical flame ignited by a spark, you should have a perfect sphere, and that in certain cases, not always, you start developing cells. This is one type of instability. Okay? And these cells can appear also on a plane of flame front, like here. You see this flame front starting to develop cells. That's another type of instability, but it's taking place at a small scale, a few thickness of the flame. When do you observe that? We didn't really talk about it, but it's controlled by the Lewis number of the diffusion reactant. Typically, it's really for hydrogen. For hydrogen, we know that it's very easy to develop these cellular flames, and you can look at the asymptotic analysis to do that, but typically, we know that the critical Lewis number is such that for hydrogen, you are below it, so you can have this cell formation. I didn't talk about that in the turbulent combustion course, but it's probable, it's quite likely that the formation of these cells interact with the cells that we form in turbulent combustion. And so there are many cases where we believe that a flame like this one has more surface than it would because some of these things here are due to instabilities, due to the low Lewis number of the hydrogen. Now, if you talk about system instabilities, the most famous one is the Pogo effect. The pogo effect is what happens if the engine gets coupled with the vibration. So if you have an unsteady heat release in the chamber, which creates acoustic waves which make the whole structure vibrate, and if this vibration leads itself directly to an oscillation of the flow rate, which leads to an oscillation of the heat release, then the whole rocket starts oscillating. And that's pretty bad. Those are low frequency, long wavelengths problems. Now, the vibrations, of course, are never good. This is an example of vibrations in an helicopter. And as you will see, it's not a good idea. So anything which vibrates in our field is a bad idea, okay? You want to avoid any problem related to vibration if you can. In gas turbines, we have the same problem because if something starts vibrating, the turbomachinery parts are very exposed to it. The distances between the blades and the casing, for example, are extremely small. If you start having vibration there and you have a contact between the blade and the casing, then the engine will explode. And you know that when this happens, it's actually a big danger. Sometimes we do it on purpose. This is a case here where you actually break a blade to see what's going to happen. You know that the blade has to stay in the engine. So this is a simulation, then you're going to see the real test. And when you do that, of course, first you lose the engine, but the big problem is that you don't want a piece of the engine to go through the engine and into the cabin, which would be, of course, a bad idea. This happens, of course, for gas turbines, but even for power gas turbines, the same problem. Siemens, for example, they know this problem. If you have something breaking, it's a piece of metal which can be big like this, flying at a speed which is Mach equal 0.7 or 8. So it can go, travel for kilometers. So it's extremely dangerous. So anytime you start having vibrations, for example, due to combustion instabilities, then you basically have to stop the engine, and then it's going to cost you. I'll talk about cycle-to-cycle instabilities. So for the moment, tomorrow. So for the moment, I want to focus on one specific class of instabilities, which are thermoacoustics. That's the result of thermoacoustic oscillations in rocket engines. As you can imagine, that was not the initial design. So if you start going that way, you have a big problem. So let's begin by saying that there's a new word today that we need to focus on, and it's acoustics. We've been talking about combustion, and we need to talk about acoustics. What's the link between the two? We know that noise is generated by flames. And the simplest example of combustion noise is a free flame. So if you have a flame like this one, blowing and burning in free atmosphere, that's a relatively simple aeroacoustics problem because this is a source of sound and it radiates to the far field and it makes noise. But if the flame is confined now, the noise is not able to leave, and that's where things begin to be dangerous, because if this noise comes back to the flame itself and modifies it, then we can have a combustion instability. At this point, I would like to remind you also about a classification of instabilities in flows, with or without combustion, which is due to Mankiewicz and Huer here at University of Southern California. And here, they put basically instabilities in two classes. One of them is called convective instabilities, the other one is called absolute instabilities. Convective instabilities are what's happening if you put a perturbation in the flow, and if you trace its influence as a function of time, this perturbation is convected away. So you put a perturbation here, and you see it going away. If you come back an hour later, everything's gone, okay? In time here, this thing will just go away. It's convected. That's why we call it convective. The absolute instability, on the other hand, is something different. You have a system, and I've shown an example actually 2 days ago during the seminar. You have a system which is stable, you perturb it, and then it starts oscillating, and it keeps oscillating all the time. And it will keep going forever. That's an absolute instability, and of course, this is what we would like to avoid. Normally, it's okay, if you add a perturbation to your engine, and after a few milliseconds comes back to stable, you're fine. But if you perturb your engine, and it does not go back to stable, then you have a problem. Note that in most cases, and that's what intuition is telling you, you can have an absolute instability only if there is a mechanism which propagates information from downstream to upstream. Why is that so? Well, if there is a flow like this, and you make a perturbation here, this perturbation goes away like this. And if there is no mechanism by which information can come back here, it's difficult to imagine how this system can resonate. You need some way to convey information from downstream to upstream. Now, there are many ways in fluid mechanics by which you can do that, but you need a mechanism. So, from a control theory system, it really means that a convective instability is an amplifier. You put a perturbation 1 at the inlet, you get a perturbation 2 or 1/2 at the outlet, while the absolute instability has actually a feedback loop. So you make a perturbation at the inlet, it goes out, but when it goes out, it sends something back by this loop here. And this loop, this system, as you know from control theory, can become unstable. And this is what we have when we do commotion instabilities. So in commotion instabilities, the usual pattern is the following. You create a big vortex that you're going to see here. That's a big vortex. This vortex burns. When it burns, it makes noise. I will be more precise in a second. This noise goes out, but it's also reflected. It's coming back here. And it's coming back here. It creates another vortex because it's changing the flow rate. And this system is a closed loop and can become unstable. Not always. Some phases and amplitude conditions must be satisfied. So in the combustion chamber, this is again, I think it's the Preckinstein engine. This one, if you wonder what is going to be able to do this for you, you see that there are many mechanisms. In a swirl flow, the flow is actually going backwards here. So it's easy for it to bring back information from downstream to upstream. And there's a second mechanism, which is, of course, that if you are in a subsonic flame, and almost all the flames we're going to describe today are subsonic, then you can have sound. If there is sound here, sound is also able to propagate upstream. So we are really in this position where there are many ways by which a flame can become absolutely unstable. So it's not surprising that we're going to have instabilities. So we expect absolute instabilities in many of these reacting flows. So, as I said, you can study many instabilities, but most of them are not as dangerous as thermoacoustics. Thermoacoustics is really the major problem, so this is why we'll focus on that one. It's not a new problem. The most famous guy who worked on that is Lord Rayleigh 150 years ago, and Lord Rayleigh already understood this coupling mechanism, and I will go back to Rayleigh in a few minutes. So let me just be a little bit more precise now about the mechanisms. If you take a free flame, you can show, actually it's a good thing to do, it's quite easy. If you write the momentum equation and you can integrate it from here to infinity, and you can show that the acoustic pressure is a function of the density ratio multiplied by some scaling parameter, decaying like 1/r, and here you have dq dt. dq dt is the unsteady reaction rate. So by the way, this tells you something. If a flame is steady, it makes no noise. Even if it's a big flame, if it doesn't move, it won't make noise. Now, if it is unsteady, it will make noise. Okay. So any flame which is unsteady will actually produce noise. And the initial paper is that one. You can go to this one. The paper by Schuller gives a very simple demonstration of this property. And you can visualize it here, where you have a flame here which is pulsated to change its shape. That's a Bunsen flame. And here what you see, these waves here are the divergence of the velocity. And you see that every time, look here, look at this point here, boom. What happened here, we had a big change in heat release because there was a pocket which disappeared. And when this pocket disappears, look at the pressure wave it is sending. This is why also we keep calling those flames monopoles, because you see the emission here really looks like a monopole acoustic source. It's like a loudspeaker, if you want. Produces sound. Every time you have dq dt, you have a wave. Okay. Now, this noise in the far field is something that you can observe easily. This is a case here where we have a simple tube. And what you hear now is just the sound of the flow here. And then if you change this system and ignite it, this is what you will hear. And the difference between the two is the combustion noise. Okay, you will see a lot of $10 experiment during this talk. We like to do that because it's cheap. That was done by my PhD student the day before his PhD defense. But that's, he actually took the spectra with his iPhone, and this is what you obtain. This is the noise that you obtain for a laminar flame. Okay, and when you have the full throttle open but no combustion, this is the noise you have. And when you go to combustion, this is the noise you have. And here you recognize what we really call broadband noise. Broadband noise means it should be broadband, no peaks. Okay, you have a noise due to turbulence interacting with a combustion. You have no resonant peaks, so it has a spectrum here which is not flat, but you don't see big peaks here. Now, if you do the same thing now in a confined domain, this flame will start doing what we just saw. It will emit waves, but then these waves will come back. Even if they don't change the flame, these waves are produced in a closed domain. So it's exactly like a music instrument. If you take any closed shape and you blow in it, you will excite the noise which can be produced. You will excite the acoustic eigenmodes of this system. So even if there would not be resonant modes, you will already, when you start blowing into this can here, you will excite the eigenmodes of the can. So you will go from a broadband noise to a place where you should see, some small peaks at least, corresponding to the eigenmodes of your system. So the first acoustic mode, the second acoustic mode, etc. They don't have to be big, but they should be there, yeah. No, if it's fully steady, if it's laminar, no problem. Okay. If it's unsteady, if it's turbulent, then you will get the broadband noise plus these peaks. Now this is a visualization actually of these waves in a burner here. We have subtracted the mean, and so you see, for example, all these acoustic waves. They are not really organized because there is no resonance. They're just produced in the burner and they bounce on the walls and they make noise, and it's okay. At that point you don't really have a problem. So the third thing, of course, is that flames produce noise. This noise can bounce on the walls, but then flames are sensitive to noise. A way to see that is that here we use a loudspeaker to force a flame. This is an experiment in École Centrale. Probably have shown that one before. And you see here how the flame reacts. Okay. And it's actually very sensitive to noise. That was observed also more than 150 years ago by people who are using candles and making music at the same time. People saw that the flames were flickering, at the rhythm of the music. So the flames are sensitive to noise, and that's of course is what we need to have a coupling. Because if flames are sensitive to noise, and if flames create noise, then you can close this famous loop. We'll have unsteady heat release creating waves. If these waves create unsteady heat release, then the loop is closed. So on the paper, it's easy. In practice, the question is, can you predict that? And can you control it? By the way, there are people who actually use combustion stabilities, for example, to make music. You can build an organ based on these ideas. So you use flames, and each of these flames can interact with its own tube, and because they create a mode which corresponds to the length of the tube, you can use it exactly like an organ. So this one is a small organ. It's only 4 notes, but some people have built, a complete music instrument with that. We use that to show students that you can do it very simply. But of course, if it happens in a real chamber, then it's a different problem. Because in a real chamber, these instabilities are going to be much more violent. And then this is where problems begin. I've shown you these pictures before. That's also a very simple flame, stabilized here in a duct. And it can do all kinds of unstable modes. That's actually one of the problems, is that it does so many modes. I lost the... You have the sound without the picture here. Well, this one does the same. Collection of sounds, okay? This is the same flame, okay? I have a problem with movies, obviously. Same flame, different regimes. Same flames again, other regime. The number of unstable regimes which a complex flame can do is amazing. I mean, it's, you are always surprised to see how many things can come up. And the most usual situation in a flame is that you have a mode like this, you do what you need to do to control it, and then it's another mode which occurs. Okay? So controlling one mode in a flame is not sufficient. If you want to control all modes, it's become a much more difficult task. So before entering now the world of acoustics, we need to discuss something else, because it is very important in most flames, it's swirl. Maybe 50% to 75% of flames are swirled, and swirl is actually a big source of problems for flames. So swirl is a simple motion that we add to the jets that we inject in the flames to improve the flame stabilization. So why do we do that? Well, because you know that if you would not create recirculation zones, you would not be able to stabilize a flame at a speed larger than the flame speed. Because if the speed of the flow is more than the flame speed, the flame will go away. The big method to stabilize a flame is to use recirculating gases. So for example here, you have a flame which is stabilized by this zone here, this is temperature, and this zone acts as a continuous ignition source for the gases which are injected. If you would not have this, you would not be able to stabilize the flame. The problem of systems like this is that the zone here is pretty hot, and you have to cool the walls, and so people have been looking for a better way to stabilize flames. So swirl is actually one way to do that. So that's a pattern of the regime in a swirl combustor for different levels of swirl. So swirl, to first order, we use a swirl number. The swirl number tells you, how much rotation you induce. So if you have a swirl number of order unity, it means that if you have an injection velocity of 10 meters per second, the rotation velocity is 10 meters per second. That's the order of magnitude. It's not exactly like this. You need to take averages because the profiles are not flat, but that's about it. So here we have a low swirl number, and when you do that, you have recirculation zone here and there, and just a normal jet. If you increase the swirl, suddenly you create a recirculating zone here, and if you increase it even more, you have a big, big bubble of recirculation here, and the gases, the fresh gases, are going around it. And so that's this situation, especially this one, is very interesting for combustion, because here you can trap your burn gases in the middle of nowhere. They don't touch walls, and you can use that to stabilize the flame. And so that's a very convenient way of going from flames which would have, would be 1 meter long, to a flame which will be 10 centimeters long, because it will be compact and confined in this zone and stabilized by the recirculating gases. So this is a visualization of a swirl jet. There's no flame here, by this group here in Paris. Patrick Huer was the guy who was first at USC, California. And you can see actually the huge bubble which is created. And by the way, you see also something else, that these flows have instabilities. Okay. And you're going to see that these instabilities, we'll have to deal with them at some point. Now, I think I've shown you this before. This is the way the method we use to introduce swirl. You can do that by many methods. Here, you just add passages which have an angle compared to the axis of the flow, and this is sufficient to create swirl. Right? Each combustion chamber has a different method to introduce swirl. That's another chamber. This one comes from the Limousine project in Europe. You can see the blades also here, the flow entering this way, and also then it has to turn actually, and so you have swirl here in this flow. Not everyone is doing it that way. Alstom has this strange design. You take a cone, you cut it like this, and then you shift it. Strange shape. The cone is here. Now imagine that this cone is in a plenum. The air is coming from here. It will have to enter this zone like this, and so it will create swirl. And depending on the size of the cone, then you will be able to have a more or less intense swirling zone here, and that's what will allow you to have this kind of flames. You can see this zone, you can see the cone here, and you can see the swirling jet, and you can see here how the flame very nicely stays in the middle of nowhere, and it's stabilized in this zone here, and it makes a very compact flame. You see, after a few centimeters, everything's burned almost. So that's really useful to have a compact flame. So that's good. The problem is that swirl is a very unstable fluid mechanism. It exhibits all kinds of problems. Not only the fact that here you have a shear layer, so you create vortices, but also the fact that globally swirl can exhibit this what we call spiral modes, and those things are a problem. You've seen swirl jets before, okay? In the sky, behind an aircraft, the contrails here are swirl jets actually. And you know that the swirl jets in the sky, they do all kinds of strange instabilities. Why is that so? Well, actually, it's not me, it's not my granddad, it's a guy called Poinceau here, a French guy, who studied the movement of rotating objects like this. And he showed that you have what we call precession, I suppose you know that. So a turning object will not turn like this, it will actually turn like this. And this rotation is called precession. Okay, so it's turning like this, but at the same time, the angle of rotation, the axis of rotation is also swirling, exactly like you see here. Now, this happens also in swirl jets, because when you have swirl, you will have these new modes which basically lead to a new type of instabilities. There are many types of instabilities. If these jets are free, like in the sky here, they create these shapes that you've seen, which we call reconnection. So the jets, the two contrails break, and then they merge with each other. That's a simulation we did of that. And you can see it actually in the sky, it gives these pockets, these puffs. Initially, you have two long vortices, and you end up with this kind of spherical or elongated objects which are cut in the middle because of an unstable mode. That's what's happening in the sky, but in a gas turbine, it's a different problem. I don't know if this thing is going to work. Yeah, you can see that, even on a plane like this, you see here the two jets, and look at the unstable modes and the reconnection, okay? Reconnection, reconnection, reconnection. So it really tells you that from a fluid mechanics point of view, every time you use a swirl jet, you have to expect, I would say, funny unstable modes. And this will be the case in combustion. In combustion, if you have not two but one swirling jet, what's happening quite often is that this thing starts precessing. And if it's precessing, what you actually see for the axis of rotation, that it will follow a spiral mode like this one. The spiral mode does not have to turn in the same direction as the mean swirl. That's where things get complicated. The flow can be turning like this, and the spiral in the other direction. It depends on the swirl intensity. Now, these things are very well captured by LES. It's actually been really the big breakthrough in a simulation probably 10 years ago. We showed that if you compute this flow with RANS, you have nothing. It's just stable flow, and you don't see this structure. If you do LES very fast and very easily, you capture the PVC. We call it PVC for the precessing vortex core. You can visualize it easily. I think some of you talked to me about the Q criterion. The Q criterion is one way to look at vortices, but you can also just plot a surface of low pressure. Pressure is low inside the vortex. This is the wet zone that you see here. That's the precessing vortex core. And you're going to see here an isocontour of temperature, which is the white zone. And the big question for the many gas turbines is to know if the precessing vortex core is in the fresh gases or in the burned gases. In this case, you're going to see that the precessing vortex core is in the burned gases, okay? It's been on the other side. It's not always like this. Sometimes the flame is not able to go into the zone where the PVC is taking place. So there is a competition all the time in those flames between the PVC and the flame itself. Why? Well, if the flame is able to come here and the PVC is not very strong, because these gases are very viscous, it will kill the PVC. Okay. But not always. It's not a rule. I will give you many examples today where it can go one way or another.
At the center of the vortices, the pressure and the velocity both are low.
The pressure is low, the velocity is not. No, the velocity is, can be high because you have rotation. Well, on the axis here, if you want to use the velocity to see the vortex, you have to use the Q criterion. Because it's not the velocity which tells you if you have a vortex or not, it's the vorticity or the Q criterion. The velocity itself, it's difficult to see it on a PVC. So, let's start now that we have the general framework, that you know that we're going to have to talk about acoustics and PVC. Let's start discussing how we're going to do that. So, I will give a lot of examples probably this afternoon. What I want to do in the morning is describe the theory for these things. The interaction between acoustics and combustion is not a classical topic in the combustion community. You go to the symposium, you have 1,400 people at the combustion symposium, you have 600 doing chemistry, and maybe 40 doing thermoacoustics. Okay? So it's a small community, but at the same time, many people come to talk to us because a lot of people have unstable modes. So I've indicated here 2 textbooks. I mean, mine is really the simplest one to begin. Once you have understood the basis, this one actually is a good one too, but that gets much more complicated. And then it's not here, but the book by Tim Lewin is also a pretty good one now if you want to do that. So how do you see combustion instabilities? Well, the first thing which happens, if you look at what we call a regime map for a flame, is that you put here the air flow rate, here you put the fuel flow rate or the equivalence ratio. You have all kinds of zones here, which tells you which kind of flames you have, and in most cases you have zones which say unstable. What means unstable? It means if you go there, you're going to start the flame shaking, and you're going to be either stopping the experiment or you see you have a problem. These unstable zones can have any shapes. You can have many unstable zones. You never know before how these things are going to look. It's actually the major problem for industry would be to be able to predict these unstable zones. Would be before you build the engine to say, okay, if you go at this speed here, you'll have a problem. You have to realize that these unstable zones can be a major headache. I'm not going to put numbers because those are classified. But if you look at, there's a French ramjet which has the same kind of thing here. So flow rate, equivalence ratio, and the map of stability is like this. I mean, which really means, you know, that you cannot go there, there, or here. You have to find your way. If you want to go to full power, which is here, you ignite your flame here. You have to do that, you know, to go there. If you're crossing something, it's the end of the engine. So that's a major problem for design, of course. You would like to avoid these things, but today we cannot predict it. So I'm going to give you an example of stability map. This is actually my PhD, so that's the one I did 5 years ago. So this is air and propane. You have a small, it's a joke. Okay, that's the window, and through the window you can look at the flame. It's a premix flame. And this flame, we operated for all kinds of regimes. And if it is stable, this is what you see. You have the jets of gases here. You have many of them. And here you have the reaction zone. And this flame, when you operate it, you can measure the noise. And you see that very rapidly you have many modes which appear here, 440, 485, 530, 590. And this is the amplitude of the mode. So if you go to that point, for example, equivalence ratio equal 0.8, you're going to have a big mode at 440. There's a zone here below where everything is stable, so you find here. If you don't go to rich flames, the flame will be stable. But if you go there, well, you will have unstable modes all over the place, okay, making noise. So what are these modes? Well, I will show you examples later, but they are some acoustic modes. So how do we study these things? Okay, basically, there are two ways to look at this problem. The first way is to say, I'm going to take the conservation equations, I'm going to find a way to solve them and solve the unsteady problem completely and find the solution, which is, of course, what everyone would like to do. But in practice, it's difficult. So there is a second method, which is trying to develop what we call stability criteria. To do that, you define an energy, and you try to find the conditions under which this energy remains bounded or not. So that looks a little bit theoretical. Let me give you an example. Okay, this problem, I guess you all know. So that's the pendulum or the linear oscillator. You have a spring, you have an object here of mass m, and the big equation now, instead of the Navier-Stokes equation, is this one. This one we can solve, okay? So m dot acceleration plus kx equals 0. This one, the first solution to solve this equation is to solve it. So you plug here the solution, you know it's going to be an exponential, you plug it here, you find the pulsation, and you know the solution is this one, so you can compute the frequency, and you can see if it's amplified or not. But there is another way of looking at this problem, is to say, well, let's not integrate this thing. Let's multiply it by v and integrate it, just to find an energy of the system. What we see here is that E is a constant. It's the sum of the kinetic energy and of the spring energy, and this thing is constant. Okay. And it does not give you the solution. It's just telling you, okay, there is something which is conserved, which is E. So in a problem like that, you don't really see why it's interesting, but suppose now that you are forcing. I tell you here that this system is forced with a force F. I don't tell you what F is. Well, you cannot integrate this thing now if I don't give you F. But for the second method, I can multiply this equation by velocity, and I find now that this energy is a constant plus the integral of Fv dt. So I haven't solved the problem, but I can already tell you something, is that if this integral is positive, you will have instability. So by the way, I'm able to build a stability criterion in two lines, and this stability criterion tells you that if you are pushing the system so that F multiplied by V is in phase, because this really means F and V are in phase, the integral of Fv dt is positive, means the phase between the two is less than pi over 2. So that's what we call an instability criterion. Okay? This instability criterion looks simple now. When I'm going to do it in 10 minutes for reacting flows, you will find it less simple. So this is here a very intuitive test. Okay, if you have a swing at home and you push your little sister, you know that you have to push when the velocity is positive. Okay, if you push when the swing coming towards you, you damp the instability. If you push when the swing is going away from you, you excite it. It's going to be the same in combustion. In combustion, the force will be the heat release, and the velocity will be the pressure. And that will lead to the famous Rayleigh criterion. I will do that a little bit later. But before I go to that, we need also to talk now about linear and nonlinear regimes. When you write linear equations and you search for an equation like that, you really search for the beginning of combustion stabilities. And if the system is unstable, then the oscillations will grow. What they will become later is another question. Because when you go to what we call the limit cycle, then the linear equations don't apply. So suppose here you have a combustor, and then suddenly you change the occurrence ratio. This thing starts oscillating. So it starts oscillating. That's the linear phase. Then it will usually go to an overshoot zone and then stabilize to what we call a limit cycle. The limit cycle is what most experiments are seeing. Okay. Remember the talk of Professor Kuchari yesterday talking about hooting. He's actually looking at the limit cycle. This can last hours. This phase here lasts a few cycles. It lasts a few milliseconds. And usually you don't even see it. Suddenly the combustor starts making noise. So the interesting point here is that this zone here, which is the linear zone, in a zone where we can write models, and but we cannot do experiments, or this, let's say it's difficult to do experiments. This zone here, where we can do measurements, is a pain because you cannot write linear models. You have to use LES or very complicated methods. So that's one of the problems we have. It's easy to do simulations here. It's easy to do experiments there. But what we would like is to compare. And you will see that this is actually a problem for the comparison here to get this done. Now, the limit cycles that you see here, that's only one form, one thing which can happen. You have to be able to resist to that. In many cases, the chamber cannot go to there. If it's a gas turbine, at some point here along this line, there is an accelerometer which is going to say, hey, you are vibrating too much, I'm shutting down the fuel. And you will shut the engine. If you don't have this kind of safety system, if it's a rocket engine, it might just explode there. And that's the end of the engine too. Or the flame can quench. It's also the end of the session. Other things may happen. So that's the first thing, okay? If you don't have a safety system, the engine will explode. The flame can also quench, and it can also move to another place. That's what we call a flashback. If you have a flashback, then you're also in trouble. So how do we know that combustion instabilities can create flashback or quenching? Well, we know it because we use active control. So let me show you this business of active control. That was a very, very à la mode, as we say in France, fashionable moment in the 90s where people started looking at that. As you know, this is the loop of combustion instability. Back in the 30s or 40s, a guy called Crocco, the guy I talked about yesterday, really a big guy in combustion, he started talking about servo stabilization of flames. He said if you have a loop like this, you can add another loop on top of it, an external actuation system, just from control theory, which will compensate this loop. How would you do that? Well, you can just measure the instability in the chamber with a microphone or a photomultiplier. Then you can process this signal and send it back to the flame. So what we're going to do is we're going to send to the flame noise produced by the flame, which is also what this loop is doing. And you see that if we do it with the right phase, we should be able to cancel this part. Crocco said that before the war, actually. But there was no hardware to do it. And it's only in the 80s that two groups did it, actually. Cambridge did it and École Centrale did it. And I'm going to show you the example here of one of the first papers. That's the one we did in École Centrale. What we simply did is we took a laminar flame here, which was unstable, and we added here a microphone. We filtered it. Then we amplified the signal, gave it to the computer, and sent it back here through the loudspeaker. What this thing is doing here is just two things. It's amplifying the signal and shifting its phase. Shifting its phase really means that if the inlet signal is like this, we're going to shift it like that by an amount phi, okay, which we will control. We can change that the way we want. So this is the result you obtain. So this is the phase of this control system, and this is the noise. You can look at the levels here. This is 200 Pascal. So even if so, it's a small laminar flame. It's making a lot of noise. 200 Pascal is already quite high. So this is the noise you have without control. And you see that if you have sufficient gain here, like for this curve, there's a range here where the flame completely stops. It's actually a very interesting experiment that you can do easily because the system we used here, the loudspeaker was coming from the car of the PhD student. And this we bought for maybe, it was just a delay line, maybe 30 euros. So that's a very cheap experiment. And so when you will be here, if the system is off, you are here, you put the system on, no noise, you put it off, you come back. So you can control the noise completely by an external system. Now the difficulty also is that you want to be careful there because if you go on the wrong phase, then you're making more noise. Okay, in the same way that you can compensate the natural loop, you can also excite it. And so it's a good system, but don't get the phase wrong. So how does this system work? Do you see it here? Yeah, it's more or less okay. So this is time. So this is the heat release. So this is the unsteady heat release of the flame. This is the pressure. And at that time, we start the actuator. So you see that the actuator, the electric system works and then goes almost to zero. And here, at the end, after 80 milliseconds, there is no noise at all, and the system is stable. More interestingly, not only it's stable, it does not consume anything. So it's actually doing exactly, I'm not sure I can do that, it's just this thing here. Chop, 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 chop. If you're good, you can just move your hand by a very small amount. Every time this thing goes left, I'm doing that. Every time it goes right, I'm doing this. So here's the same. Every time the flame, you don't see here, but if you would zoom here, you would see this very small activity. So the system monitors the oscillations, and if the flame starts going one way, hop, you change it the other way. And so it was a very exciting idea, because that means that for zero cost in energy, you were able to control the flow completely. And that's so everyone started taking patents on that. I have 2 patents on that. The English have another one. GE has another one. Siemens started to fight us not to pay for our patent. So it was a big deal. So we did demonstrations on real engines, even on turbulent flames. And Siemens actually even did it on a real turbine. Okay, there's a big demonstration here in this paper by Sömer. You can get in this journal. They installed on a 24 burner system a full instability control system. The cost was of the order of 1 million euros, so it was very big, but it worked. We were able to do it. But the problem was the cost. The second problem was the big discussions we had with GE. The paper you saw here, this paper here, was completely replicated by GE. So GE did exactly the same experiment we did, and then they took a patent, which is typical of GE. So, unfortunately, they didn't know that we already took a patent, but then they told us, you can sue us, no problem. We have 2,500 specialist lawyers, and then we said, okay, well, it's too bad, because CNRS in France doesn't have the capacity of fighting this kind of guys, so forget it. I never became rich, so that's what it means. Because in any case, the big problem was not the patent, the problem was the certification. When we started talking to the engine guys, they said, hey, we are not going to put a system like this one with a closed loop on an engine, because if your closed loop system gets crazy, it's going to make things worse. Or if your closed loop system breaks, it's not going to work. And we don't want closed loop systems, on a fighter maybe, but on a civil aircraft, personally, I'd rather not fly on a system which has this kind of things, okay? Because you rely on the sensors. If the sensors get crazy, it's too complicated. So in practice, we knew that the idea is pretty good, but it's not going to fly, okay? It's not going to fly. But for us to do research, it's still a very interesting methodology. Note also that compared to what Professor Kushawi presented yesterday, he was presenting, he called them active control, but that was not closed loop, okay? It's an open system. This is closed loop. This is what makes it more efficient, but also more dangerous. Open loop is probably safer. Open loop, you don't have to worry about the phase. Now, what you can do is you can use it the other way now. If you have a system which is controlled, here the control system is on, at time t equals 0, you can release it, and then you can see the instability growing. And you can study it, you can even measure the growth rate. So we use it to do this kind of studies. So let me give you another example. What I've showed you was a small, maybe 5 kilowatt laminar flame. Now this is a 200 kilowatt turbulent flame. Now in addition to the laminar flame, we have to handle turbulence, which is a problem in terms of signal processing, because in addition to the commercial instability, we have the turbulent noise. So how we did it here, we measured here with a microphone the noise. We go through the delay line, through a loudspeaker, and here, in a system like this, which was a diffusion flame, the smart thing to do is not to excite the air, because that's a big flow rate, but just to excite the fuel. So we are actually pulsating the fuel injection, and only the fuel injection, which is like 20 times less than the air. So you can use much smaller systems. When you do that, you can diminish the noise by about 24 dB with this system, where if you have the right delay line. So this is without control. This is with control. You see the 2 peaks here, 24 dB. So basically the noise goes away. 24 dB is quite a large amount. So here also it works. Now, when you do that, you can go one more step. This is what we call stability maps again. And the stability map without control is here. Everywhere here, you can operate this flame. So you have a propane flow rate here, air flow rate here. You start the flame, it's going to burn, and it's going to be stable. If you go in the red zone, then it's going to start oscillating. And if you go in the black zone, it's quenched. It's gone. Okay. Now, this is without control. If you use active control, this is what you find. All the red zones disappear. You can control all the points. But there is an interesting point here, is that point A, which was unstable, becomes stable. But point B, which was quenched, there's no flame here, becomes a valid flame point. So that really means that this point B now can burn with control, and it could not burn without control. So what do? You put the control on, you go to that point, and then you switch the control off, and you look at what's happening. And this is the scenario that you find. So here the control is on, the flame is burning, you switch the control off. This flame is unstable, so it starts oscillating. But there is a limit to what a flame can sustain when it starts oscillating. It can self-quench, if you want, because it's oscillating so much that at some point all the burn gases go away. There is no fresh gases left in the engine, so when the new gases arrive, they don't ignite. And so you see here after maybe 100, 200 cycles, shoop, suddenly the whole thing stops. It doesn't take long, okay? It takes half a second. So if you sit in front of the experiment, you don't hear anything. Half a second is not long enough. So you just say, oh, my flame is quenched. No, actually, the flame is not quenched. It goes unstable, and because of the instability, it quenches. So that's an example where instability actually creates quenching. You don't even know it. That's why also many people are surprised, because if you look, for example, at the flammability limits of methane, they say it's 0.6 to 1.4. But then they say, well, my engine quenches much before that. It quenches at 0.7. Well, very often it quenches because it gets unstable. And when you talk to people looking at quenching, most of them will tell you, before flame quenches, it starts, oscillating. You see it or you don't see it, but in most cases it's there. So that's a proof that you need to understand combustion stability. So this is noise, and this is heat release, going to zero. Okay, the other advantage that I'm not going to talk much about it today, of course, is that in this zone here we can measure the growth rate and use it to validate models, while in this zone, here it's only experiments which you can use, but with this system of active control you have access to this part here. Okay, another possibility now is flashback. Flashback is a fascinating phenomenon where the flame, instead of staying where it should be, goes to another place upstream in the chamber. You've seen some examples also in Professor Kushawi's talk yesterday. When this happens, usually the engine is dead after a few seconds. So let me show you one example here. That's a pressurized burner installed at École Centrale here, where you have a nozzle at the outlet. Pressure goes up to 2 bars approximately, and this system is very unstable. And we told them, before they built it, we told them this thing is not going to work, it's too unstable. You are injecting gases here, they are premixed here, and here the flame is supposed to be here. So we did the simulation before they did the experiment, and we told them what's going to happen is this thing. So this is the mesh. What's going to happen is that this is the flame surface colored here by velocity. This flame here is not going to stay where it is. It's going to flash back. So how does it do that? It gets coupled to the acoustics. You have here the pressure, 2 bar, 2.5 bar, and you see that this flame starts oscillating and coupling with the acoustic modes, so it's flashing back and getting in and out, in and out. And after it does that for sufficiently long times, it will completely flash back. It takes a while, again. Now you see at some point it will flash back, and then it will get stuck. Now, chook. Now it's stuck at the other side, so it's stabilized. It has found a stable position upstream.
So these equations are inherently unstable, right? The equations which are
No.
governing this flow gravity.
Well, yeah, exactly. For this case, it's unstable. It's not always unstable. It's only this case which is unstable.
So when you do a numerical simulation, you will never reach the first point. T equal to 0, you will never reach a steady state, for example.
Yeah,
And
that the problem is to do that, you first have to find the steady one which is stable, and then you go to this regime, because otherwise you cannot have a stable point here.
So T equal to 0 actually there's a shift in the parameter.
What we do at T equals 0 is we add the nozzle. here, if you do the simulation without nozzle, this flow is stable. We are able to stabilize it. We put non-reflecting boundary conditions. We have a stable flame, and then at t equals 0, we add the nozzle, and then this thing goes away.
That also actually changes the green flow. So green flow also is changes and
We assemble, we do actually, we cut it here, and we do a simulation of the nozzle for steady flow, we do a simulation of the flame for steady flow, we connect them, and if it would stay steady, it would be a consistent solution, but it's right away, it starts oscillating. But you're right, there is a problem of initial point. Actually, when they did the experiment, what happened is that they would start the experiment, and after a few seconds, they would see that the temperature here in DNet was going to 1200 K, and they had to stop it. So we did not have access to the exact methodology, to the exact sequence which leads to flashback. The only thing we can say is that there is no stable point here. As soon as you put the nozzle, the flame flashes back. So that's another thing which may happen when you have this type of instabilities, quenching, flashback, vibrations, all these things that you don't want to have normally. Well,